Hey, welcome back. In this segment, we're going to keep looking at pandas and move on to the DataFrame object, which is the format that corresponds to CSV files and spreadsheets. So let's say that you have three pandas series objects. We can easily join them to create a pandas DataFrame object. In fact, you can join any number of series objects using pd.concat, listing the series here, and then specifying axis equals 1 to concatenate along the columns, to join the columns. And know that if the indices are different, such as in this example over here, you can still concatenate multiple series objects. Pandas will respect these different index values, and it will join the series by aligning the indices. If you specify join equals outer as an argument, pandas will do this. It will create a data frame large enough to hold the data from all the series, and it will fill in any missing data values using nands. Now, if you specify join equals inner, it will create a data frame that only has index values that are within all the series you're joining. But you don't actually have to start from series to create a data frame. You can just create one directly. And we do that using the pd.dataframe function, which takes the index, a list or 1D numpy array, and the data. And here you specify the data as a dictionary. If you remember from Katie's lesson number 6, dictionaries are defined using curly brackets, and they have key value pairs that are joined by colons. So in this case, each key is a string representing the column name, and each value is a list or array representing the data. So in this example from our first segment, we've created this new data frame called df, using this index of years and this data dictionary of temperature and salinity data. And there are a bunch of ways that you can get useful information about a data frame. You can print its shape, which gives us columns and rows, similar to NumPy, or its size, similar to NumPy again, which gives the total number of data values. You can also just print the data frame, print df here. But with a lot of data, this isn't the best option. It's fine here. Using Python's display function actually is a lot better, and that shows this much prettier view, which for larger data frames is more interactive. You can scroll through it, and that makes it really useful for big tables. And lastly, using this function .describe, calling that on a data frame, that pulls up this nice table here showing for each column, so temperature and salinity values, the number of values, the average values, the standard deviation of the values, the minimums, the 25th percentile values, the 50th percentile values, and this one is the median here, the 75th percentile values, and the maximum. Okay. And just like with series, you can get the index as a NumPy array by calling .index.values on a data frame. You can also get the column names as an array by saying .columns.values. And you can get the entire data, which is usually a two-dimensional NumPy array, by just saying .values. And here we get that 2D array. But here's the one that's different. Because data frames have more than one column, you can select a column of data using dictionary-style brackets indexing with a column name as a string here. And that gives you back a series. Now, often we want the series data as an array. So for that, we'd add .values at the end. And here we get that NumPy array of the values. Okay. And we can use the same syntax for indexing as with series, using .iloc for selection by index or indices, and .lock for selection by label or labels. And this selects data in all the columns in certain rows that you're specifying. We can also specify a certain column or columns and index into those using .iloc or .lock. So in this example here, we say df, the name of the data frame, or name of the data frame here, brackets, salinity, which is the column label, then .lock, brackets 2019, which is the index label. So we select the column here and the row over here. And here's where pandas becomes really useful. You can apply almost any NumPy function, such as mean, to a series or a data frame object. And without any arguments, it applies the function along the index, which is axis 0. So these give the same thing here. In the case of our running example, df.mean gives back a series with the average temperature and the average salinity. Now, on the other hand, if you specify axis equals 1, it applies the function along the columns. So here you get the average of temperature and salinity for each year. And lastly, you can use this option skip NA equals true if you have missing data, so NaN values, that you want to be ignored when you do this NumPy calculation. So to put it all together, say you have a big data set with lots of parameters, one of them being salinity, and you want the average salinity from 2017 onwards. How do you do that? Well, you start with the name of your data frame, then you use brackets indexing to select the column, then you select the rows that you want using an index label, and here we're using some open-ended slicing for 2017 onwards to present. Then you stack on this NumPy function at the very end. So you have this chain structure where you start with the data frame, you get a series from here, you add in the dot lock indexing, and that gives you a slice from that series. And then finally, you apply the mean function at the very end to reduce that series to a single value, the average. And this style of writing Python code, it probably looks pretty different from what you're used to, but that's intentional. It's meant to be really compact so that you get more science done while writing fewer lines of code. It also makes your code more readable. And the benefit of that is that you'll make fewer errors, you'll have fewer bugs. And when you look back at your code a few weeks or months later, it will hopefully be easier to understand what you were trying to do when you wrote that code. And this is the philosophy behind Pandas, as well as the X-ray package that I'm going to introduce next. And just as a demonstration of this with Pandas, imagine you want to, you have a bunch of data, and that corresponds to a bunch of date times. And you want to calculate the average value over all date times in 2019. Well, here's how you do that using a for loop. Here's how you do that using NumPy. And here's how you do that using Pandas. And which of these is easiest to understand? I think it's Pandas, which you can read almost directly, right? For the data at the index locations for 2019, take the mean. And that's it, you're done. As a side note, I actually didn't introduce this particular shortcut for indexing yet, but what it does is it lets you use a string containing a year or a year and a month or a full date when your index has date time objects. And it's really intuitive and useful. So to finish up this lesson, I just want to emphasize that Pandas is the way to go when you're working with tabular data or spreadsheets. And by that, I'm referring to CSV files, comma-separated value files, and Excel spreadsheets. You've seen in this lesson how capable Pandas is compared to NumPy when it comes to interacting with tabular data. And I'm also going to demo this with real data in class. And Pandas offers a lot of really powerful functions to work with these files. So to save a data frame to a CSV file, you simply call the function toCSV with the underscore here on the data frame variable, and you specify the file path, including the file name where you want to save that file. Now, to read a CSV file into Python as a Pandas data frame, you call the function pd.readCSV, and that can handle .txt files as well as CSVs. So similar to NumPy's gen from text function that you saw in previous lessons, you give the file path with the file name, you give the delimiter, and you give the number of header lines to skip. But note that if the values in your file are separated just by white space, you should set this delim white space argument to true, and you should not specify this delimiter argument. And here's a link to the API, the documentation, where you can find more parameters to customize how you read in these files. And just to emphasize again, this function and the Pandas package in general, they're just much more capable and I think easier to use than NumPy for working with tabular data because they give you those aligned, these aligned rows and row and column names that you can work with. So in my experience, I found honestly very few reasons to read a CSV using NumPy rather than Pandas. And just one last function here. You can also read Excel spreadsheets using Pandas read Excel function. And the main difference with read CSV is that here you don't have to specify a delimiter. Excel has their own format for that. And you should specify which sheet name inside the spreadsheet you want to load. And of course, there's also a pd.to Excel function that saves a data frame to an Excel spreadsheet if you want to do that. Last slide here, if you're ever stuck with anything related to Pandas, strongly encourage you to check out their online documentation. They have a nice set of getting started tutorials and a full user guide as well. And I found that all of it is really easily read and accessible. And of course, what I covered today is just a tiny sliver of what Pandas can do. So as you work on your final project and do research beyond this course, keep exploring Pandas because this package really makes it so much easier to analyze data in Python. And that's it for this lesson, or this segment of the lesson. Make sure to check out the next two segments about Xarray next.